students, now we are going to talk about elimination reactions. This chapter again we have divided into three modules. The first module we will be introducing elimination reactions, and we'll see all the details of E1 mechanism, that is E1 elimination reaction. So in this particular chapter we have got all the details about elimination, different mechanisms, how they take place, and their comparison, and what are the different factors which will decide by which mechanism this particular reactions will go, will be discussed in this particular chapter. So at the end of this particular chapter you should be able to understand what is elimination, then what is base, what is leaving group, how it affects the course of the reaction, as well as how structure of the reactant is important when we decide what mechanism the reaction will follow during elimination reaction, as well as we'll be talking about the stereochemistry of this particular various types of reactions. So first we'll begin with the introduction part. Now already we have studied about the substitution reactions, and we had seen that substitution means replacing one atom or group of atoms by some other atom or group of atoms. So there we were replacing some atom or group of atoms, and we have seen that in those reactions that your sp3 carbon was converted into sp2 if it is SN1, and then again back to sp3 carbon. Now elimination reactions, as the name indicates, something is eliminated, right? So there is a loss of molecule from the reactant to give the product. In doing so, what happens now that sp3 carbon is converted into sp2 carbon. Mostly a carbon to carbon single bond is converted into carbon to carbon double bond. Then we will call that as a elimination reaction. Now there are many types of elimination reactions are there, like 1-1 elimination, 1-2 elimination, and again different mechanisms are followed. But most common elimination reactions are called as beta elimination reactions. What is it and how they take place? We'll see the details. One example is written here. You can see now here cyclohexanol is there, and this cyclohexanol is converted into cyclohexene by loss of water molecule. So OH from this particular carbon, and next to that, if I remove hydrogen from this particular carbon, a double bond will be created between these two carbon, and we'll say that this is an example of elimination reaction. Let's take this example. Now here, in this elimination, the leaving group is and your electrophile, they're attached to same carbon, and therefore such kind of elimination are called as alpha elimination reactions, or they are also called as 1-1 elimination reactions. So with this we get carbene type of species are obtained, or nitrines are obtained by alpha elimination or 1-1 elimination reactions. There are some other reactions where cyclization takes place and you get a ring compound. So in this cyclization, you may get 3-membered, 4-membered, or 5-membered ring as a product by various elimination reactions, maybe gamma elimination, delta, epsilon, depending upon what is how many number of carbon atoms are there between the eliminated groups. We will classify them as alpha, beta, gamma, delta, and so on. But now we are going to focus on beta elimination reactions. They are also called as 1-2 elimination reactions because here the eliminated atoms or group of atoms are adjacent carbon atoms, and therefore it is called as 1-2 elimination reactions. Now depending upon the substrate structure, type of base, as well as leaving group size, we can have 3 different types of mechanisms of these beta elimination reactions, and therefore as per the mechanism we can divide these into three classes. Reaction, elimination reaction, which follows one-step mechanism, is called as E2 elimination, and those which follow two-step mechanism are either called as E1 or E1CB reaction. So one by one we are going to see the details of E1, E2 and E1CB mechanism. So let us focus first on E1 elimination. Just like SN1, the 1 stands for unimolecular, in E1 also 1 stands for unimolecular. So it is a unimolecular elimination reaction which occurs in two steps. What are the two steps? So you have a leaving group, just like in your SN1 also you had a leaving group. And generally here another group which is lost, or another atom which is lost from the substrate, is hydrogen, which a leaving group attached carbon is called as alpha carbon, and next to that we have beta carbon. So first, when this reaction takes place, in the step 1, which is called as a rate determining step or a slow step, a carbocation is formed. We know that whenever carbocation is formed, the hybridization changes from sp3 to sp2 hybridization. Now it is a planar carbon atom. Now here the hydrogen from the beta position is lost, and you get a product where now a double bond is formed between your alpha and beta carbon atom. So a sp3 carbon is converted into sp2 carbon due to elimination reaction. So this is how we summarize the two steps of E1 mechanism. But you'll find that in a slow step you have only substrate involved. The base comes into picture in the second step, where abstraction of beta hydrogen is done from base. So the rate of the reaction depends only on the concentration of substrate and not on the concentration of base, and therefore we call this reaction as a unimolecular reaction, because even though there are two molecules which are taking part into reaction, the rate of the reaction is independent of the concentration of base. It depends only on the concentration of substrate, and therefore E1. So just like SN1, E1, where carbocation is formed, and then second step beta hydrogen is removed to give you a unsaturated product, that is a carbon to carbon single bond is converted into carbon to carbon double bond. So I can always summarize this reaction in two steps, where now generally alkyl halides undergo such kind of reaction where X is attached to alpha carbon atom. It departs from the substrate to give you carbocation, and base removes hydrogen from beta carbon atom to produce a product where a double bond is formed between alpha and beta carbon atom. So it is found that the first step goes through via a transition state, and this first step is a slow step, which is endothermic in nature. The second step is fast and exothermic in nature. Let us see a three-dimensional view of these molecules and understand our E1 elimination reaction. This is my substrate. This particular is a living group. This pink ball indicates a living group. And this is my alpha carbon atom. This carbon is attached to 1, 2 and 3 groups. These are beta carbon atoms, and this is my alpha carbon atom. Now what happens in the first step? The living group will depart from the substrate. So your living group is going, and a positive charge is formed on alpha position. Now this carbocation carbocation has positive charge, and the base approaches this carbocation. It takes up one of the proton from beta position and removes this beta hydrogen to give you an unsaturated molecule where alpha and beta position, now a single bond will be converted into a double bond, and you get a unsaturated molecule as a product during this elimination reaction. So this is your leaving group, this is your base with the hydrogen, and this is your product. You can see that there is a double bond now between alpha and beta carbon atom. So if I draw energy profile diagram, you'll find that there are two maxima. The first transition state falls into a carbocation intermediate, then goes to a second transition state, and then give you a stable product. Product will always have lesser energy as compared to reactant. If I write a rate equation, the rate depends upon only on the concentration of substrate, that is alkyl halide over here, and therefore it is unimolecular elimination reaction. Let's take another example now. In this particular now reaction, what you'll find, first of all, you have to look at a living group. So which one is a living group over here? Br is a living group. So what will happen in the first step? Br will depart from substrate and you will get a carbocation. This is a tertiary carbocation, so it is a stable carbocation. Now, if you have a base, then that base will abstract a hydrogen from beta carbon atom. Now this is my alpha position. There are two alpha carbon atoms. Sorry, there are two beta carbon atoms, and hydrogen will be lost from one of them to give you a product. Now here you get a double bond between alpha and beta position, and you get the product. Here you can see a unsaturated product is formed from saturated substrate. If I carry out the kinetic study of this reaction, what you'll find, if I double the concentration of alkyl halide, the rate of reaction also gets doubled. You can see here that if I go on increasing the concentration of substrate, the rate of reaction is increasing. That is, there is a linear proportion between the concentration of substrate and the rate of reaction. But if I change the concentration of water, I go on increasing the concentration of water, but there is no effect on the rate of this E1 elimination reaction, which again indicate that the concentration depends only on the concentration of the rate of the reaction depends only on the concentration of substrate and not on the concentration of base, therefore unimolecular. Let's take another example. If I take 2-bromobutane and carry out this reaction, you get a carbocation. It's a secondary carbocation. Now in this secondary carbocation, I can remove hydrogen from this beta position, or I can remove hydrogen from this beta position. Let us call this as a beta 1 and this as a beta 2. So whenever base will approach, if a beta 1 hydrogen, that is this, is lost, then I'll get this as a product. Okay, so what is the name of the product? 1, 2, 3, 4 and 5. It is a pentene. But which pentene? It's a 2-pentene. And if my beta 1 hydrogen is lost, then I get a terminal alkene 1, 2, 3 and 4. Again it is a pentene, but this is 1 pentene and this is 2 pentene. So these are the two expected products because we have got two types of beta hydrogen atoms, but out of which one is major, other is minor. The generally more substituted alkene is obtained as a major product because it is more stable. Now what is more substituted? If your olefinic carbon atoms are attached to less number of hydrogen atoms, then it is called as more substituted alkene. If I count the number of hydrogen atoms attached to these olefinic carbons, this is one hydrogen and there is one more hydrogen attached to this. In total, there are two hydrogen atoms attached to these olefinic carbons. If I come here, then I know that the double bond is between these two carbons. Two hydrogens are already attached to this particular carbon and one hydrogen. So there are three hydrogen attached to olefinic carbon. So this is less substituted alkene and this is more substituted alkene. More substituted alkene will be obtained as a major product. If I take another example, again now here you will see that this is my living group. So the living group will depart and you will get a carbocation. This is again a secondary carbocation. Now this is treated with a base. Let's say methoxide is a base over here. This methoxide can take up this particular beta hydrogen to give you a product that is 2-methyl-2-butene. Or there is one more possibility that this CH3 is beta position and can lose its proton. So if it loses, you'll get this as a product. So you are expecting two products. One is 2-methyl-2-butene another is 3-methyl-1-butene. Now you can find out that which is a more substituted. So here you can see this is a terminal alkene. Terminal alkene will be always less substituted as compared to these alkenes where your double bond is in the carbon chain. Will be always a more substituted alkene. So out of these two, this is more substituted alkene, and therefore 2-methyl-2-butane will be obtained as a major product, whereas 3-methyl-1-butane, which is less stable, which is less substituted, will be obtained as a minor product. Another example, if I see, even reactions are generally stereoselective reactions. Stereoselective reactions where one is obtained as a major product. You get two products, but one will be major and another will be minor. So just now we have seen some examples. Let us see one more example. Here my Cl is a leaving group. So obviously this is going and the beta hydrogen will be removed from this carbon. Now this particular carbon is also beta position, but there is no hydrogen attached to this carbon. So there's only one possibility you'll get this. But then this particular compound can exist in two forms. One is a trans, another is a cis. So this is a trans form and this is a cis form. Which one will exist? So you'll find that both will exist. But since cis is sterically crowded, highly unstable, this will be a minor product, whereas trans will be obtained as a major product. Trans is also known as anti, and this is syn. Anti will be a major product, and whereas your cis will be a minor product. If I take this example now, this OH will be converted into a good leaving group whenever acidic medium is used, and you will get a carbocation at this alpha position. Now again there are two possibilities. This is beta and this is also beta. So if this beta is lost, a double bond will be formed between these two carbon atoms and you'll get this as a product. And if this is lost, this is another beta position where hydrogen can be lost, you'll get this as a product. Now what you find, this also exists as a cis and trans, but trans will be a major and cis will be a minor because this is a sterically crowded molecule. It is making it unstable and therefore this will be obtained as a minor product. So we will say that E1 is a stereoselective reaction. Now, what you will find that what kind of substrate generally undergo even elimination reactions. So you'll find that the first come as a structure of substrate, tertiary alkylalides generally undergo even elimination. This is very simple. We have seen that these factors in SN1 also, that they will give rise, tertiary substrates will give rise to a tertiary carbocation. And we know that stability of carbocation decreases if I go from tertiary to secondary or secondary to primary carbocation. So generally primary substrates, primary alkylides will never undergo even elimination reaction. E2 depends upon the what groups are attached to carbocation, these are, and tertiary will always undergo your even elimination reaction because they give rise to a stable carbocation. Who makes the carbocation more stable? We have discussed this in lesson 1 also. So there are two factors. One, a positive inductive effect, and second one is a hyperconjugation. Because of that, tertiary carbocation becomes more stable as compared to secondary and primary carbocation. Once a carbocation is formed, then actually four things can happen. What can happen? So it can react again back to a leaving group and give the starting material, or it can react with nucleophile and give the substitution product, or it can lose a proton and give you elimination product, or if your carbocation is less stable and by rearranging, if you're getting more stable carbocation, then that can undergo rearrangement. So this intermediate form have various reactions it can undergo or various mechanisms it can undergo depending upon reaction conditions. So another thing, now we will be talking about structure of the substrate. In that we have seen the alkyl part. Now we'll see the leaving group part, because your substrate is made up of two parts. One is alkyl part and another is the leaving group part. Now what you'll find that your living group has to be a good living group, then only this reaction takes place at a faster rate. For example, hydroxyl is not a good living group. So if I carry out this particular reaction in acidic medium, it undergoes protonation, and after protonation, now this particular group, oxygen carries positive charge, becomes a good living group. And then this will depart and you will get a carbocation. Once this carbocation is formed, then beta hydrogen will be lost and you will get alkene as a product. So another prerequisite is that you need a good living group for even elimination reaction. Selectivity, even reaction usually favors most stable alkene, and as we know that highly substituted alkenes are more stable, and therefore that will be obtained as a major product. This product is called as Saytzeff product. I think in SYBSE we'll study a little bit about Saytzeff. We'll be seeing more details about Saytzeff and Hoffmann products in the second module. So we understood that generally more substituted alkene will be obtained as a major product, as well as if it exists in two forms, trans and cis, trans will be a major product and cis will be a minor product. Let's see again what are the different factors. So this is your primary, secondary and tertiary carbocation will be obtained. So they react at a faster rates. How they react? So if this is a green living group, sp3 is converted into sp2. Now there is a positive charge on this particular carbon, and now the base will come to this particular carbon. This is beta, this is beta. So what are the, how these reactions will occur? Now hydrogen can be lost from here, hydrogen can be lost from here. So two possibilities are there. This is a terminal alkene you will get if I lose this hydrogen. And if this hydrogen is lost, then you will get a more substituted alkene. So obviously this product will be a major product and this will give you a minor product. So this is how here two products are expected. This is your terminal alkene and this is your inside double bond alkene. This will be a major product. So depending upon the orientation, what hydrogen, what type of hydrogens we have, so you'll find that as the number of alkyl groups attached to this olefinic carbon goes on increasing, the product becomes major, and you can see now highly substituted alkene will be always a major product if I compare with other alkenes that are less substituted. If I've got these two products, then trans will be major. Let's see the structures again. So what you'll find that this is cis, this is trans, trans will be major, cis will be minor. This is another example where this red bond is a leading group. Again, sp3 is converted into sp2 carbon, a planar carbocation is formed, and then it has to undergo elimination. Now there is no hydrogen over here, so the possibility that it might undergo rearrangement to give you the product. So again, elimination takes place and you get the product. So this is how you can summarize the elimination reaction E1 mechanism. So what you'll find that E1 always competes with SN1 type of reactions because more or less the mechanism is same. And then sometimes you find that whether E1 will take place or SN1 will take place because there is a competition between these two reactions. If I take this particular substrate t-butylbromide, I know it's a tertiary, so it will form a stable carbocation. After formation of stable carbocation, in presence of ethanol, whether it undergoes elimination or whether it undergoes substitution. If it undergoes elimination E1, you'll get this as a product. And if it undergoes SN1, then you'll get this as a product. At that time, it will act as a nucleophile. And you'll expect these two products as a E1 and SN1. So what you'll find that if I carry out this particular reaction at a higher temperature, you can see here heat. Okay, if the reaction is carried out at higher temperature, then it is found that E1 product will be major, SN1 will be minor. But if the same reaction is carried out at lower temperature, then SN1 will dominate over E1. That is, SN1 will be a major product and E1 will be a minor product. Similarly, there are certain rules, like for example, if you have a cyclic moieties and they undergo, let's say, elimination. The first step is elimination to give you a carbocation. Now this particular carbocation is at the bridgehead. And because of that, what will happen, if it want to lose its proton from beta position, the beta position is here, here, here. It is symmetrical. It can be lost from anywhere. So a double bond either will come between these two carbon, or these two carbon. But what you'll find that according to this particular Bredt's rule, a double bond is not allowed at the bridgehead. So this product is not stable product. It will never be formed, and therefore such kind of substrate will never undergo E1 elimination. Rather, it will undergo substitution reaction where nucleophile will come and form the product. So, under certain conditions, then we have to see whether the reaction will take place uh, as an elimination or it will undergo substitution reaction. So here we finish with the even elimination reaction and we have introduced what is elimination. These are the few questions with based on whatever we have studied today. You are supposed to answer this question and try to justify your answers. In the next module, that is module 2, we'll be talking about E2 mechanism. We'll be talking about what is Saytzeff, what is Hoffmann product, as well as we'll be talking about even versus E2 mechanism. Thank you.